So while the log mean temperature difference approximation is useful when the inlet and outlet temperatures are known for a heat exchanger, it's not something that's easy to use if you only have, for example, the inlet temperatures. So if you only had the inlet temperatures, then the LMTD approach is iterative if you wanted to calculate the outlet temperatures for a given heat exchanger. An alternative is the Effectiveness-NTU method, which allows us to directly find out what the outlet temperatures are in terms of the effectiveness and the number of transfer units. To understand this approach better, let's think about the derivation of it using some of the things that we already know from the LMTD approximation. So we know that globally the heat transfer rate Q dot can be specified both in terms of the temperature difference for the hot stream or in terms of the temperature difference for the cold stream. The important aspect here, recall before we go further, that capital C is mass flow rate times the specific heat capacity. So when we say that CH, for example, that's the mass flow rate of the hot stream times the heat capacity of the hot stream. The important aspect of this problem is that we have to identify the minimum between the hot stream and the cold stream. And the reason for this is actually quite simple. So imagine a relatively simple problem where we have a temperature distribution. So we're going to have a heat exchanger system where we have the hot fluid coming in at the left and going to some temperature at the base here. So this is T hot out. And we have the cold stream going to T cold out from T cold in. So as we increase the heat transfer coefficient between these two, so we're going to increase UA. So this is for a fixed UA. As we increase the heat transfer coefficient, what you see, or what you would imagine, is that there's more transfer that potentially happens. So this is increasing UA changes both the hot stream profile and the cold stream profile. And in some sense, what we want to understand is that for a particular UA, for the maximum possible UA, the best that we can do is to take one of these temperature distributions and have it such that at its outlet it equals the inlet temperature of the other stream. The one that's going to happen for is the one that has the smaller mass flow rate times heat capacity. So if the cold stream had the smaller value of this mass flow rate times heat capacity, as we increase our heat transfer coefficient times area, at some point we would imagine that it could reach this TH inlet value. So what we understand is that there is a minimum flow rate consideration, a minimum flow rate heat capacity for one of these two streams. This is a two-stream problem, and we want to track and understand which of these streams is that minimum. So remember that the effectiveness can be defined in terms of the heat transfer rate divided by the maximum possible heat transfer rate. Given what we just said, we say that the maximum possible heat transfer rate is going to be the minimum value, the flow with the minimum value mass flow rate times heat capacity times the maximum possible temperature difference across the problem. So this is the maximum delta T in the heat exchanger. Now, as far as the numerator is concerned, we can talk about the heat transfer rate either in terms of the hot stream and the temperatures in the hot stream, or in terms of the cold stream and the temperature differences in the cold stream. Well, for this particular problem, we're going to assume that the cold stream is going to be the one with the C min eventually. That's going to be the way to think about this. So knowing the integration of delta T for a parallel flow heat exchanger, so we're going to think about a parallel flow heat exchanger at this point. So remember, the parallel flow heat exchanger problem is one in which both streams are going to each other. So we have a hot stream in and a cold stream in, and this is some length L. This is 0. So when we did the integration of the delta T equation for the parallel flow heat exchanger, we got this in terms of, we talked about in terms of epsilon NTUs, but we just remember that the basic integration results in this formulation. So this was our d delta T dx equation. So let's remember that equation. So we had d delta T dx was in terms of minus UP 1 over CH plus 1 over CC times that delta T. And then when we integrated it, we had this equation. If we simply factor out CC, then I hope you see that we have 1 plus CC over CH. That ratio is called the capacity ratio. So it's C min over C max. And NTU, of course, is the number of transfer units. So for the case that C cold is the minimum, we have that TH out minus TC out over THN minus TCN, which is really the argument of this log, is equal to the exponential of minus NTU times 1 plus this capacity ratio. Now, just using the overall global heat transfer rate model, so this is the global balance, we can easily solve for TH out in terms of TH in and the capacity ratio. So what you see here is we divide through by CH, define RC to be CC over CH, and then solve for TH out. If we substitute this into the exponential equation, and by exponential equation I mean this, then we get THN minus Cn. So this Cn, we introduce this minus Cn plus Cn just to make things, so we introduce this to simplify the analysis. So we haven't added anything because we subtract it and add it into this equation. But when we do this and we divide by TH minus TCN, so we're back to this exponential equation. This exponential equation says TH out minus TC out over THN minus TCN is equal to the exponential of minus NTU 1 plus RC. We substitute TH out in this form there, and what you see is that we clearly get, and this is going through a few substitutions, but we get 1 minus RC epsilon minus epsilon is equal to e to the minus NTU 1 plus RC. These epsilons are TC out minus TCN over THN minus TCN. So let's go back to make sure that this is our definition for epsilon. So epsilon, for the case of C cold is C min, is TC out minus TCN over THN minus TCN. Okay? The THN minus TCN divided by the THN minus TCN in the denominator is just 1. The TC out minus TCN over RHN minus RCN is epsilon, so it's times on RC. And we have it again, minus epsilon is equal to minus NTU. Again, this is the case of CC is the minimum. we have epsilon. This is really, I could have just stayed here. For the case that CC is C min, we're just looking at this. So epsilon is TC out minus TCN over THN minus TCN. This is what I just wrote up here, where we factor out the epsilon, and now we can solve. So this is factor out epsilon, and we can now solve for epsilon. Solving for epsilon, we find that epsilon is just in terms of the number of transfer units and the capacity ratio. For a given heat exchanger with known size, which is the number of transfer units, and this capacity ratio, we know epsilon. If we know epsilon, then, and we know the inlet temperatures, we know the outlet temperatures. So given heat exchanger parameters NTU, RC, and inlet temperatures, we calculate epsilon, and using epsilon, calculate the outlet temperatures. If we were to design a heat exchanger with a given outlet temperature or effectiveness, then typically the thing that we have to do is figure out what the size of that heat exchanger is, and that means that we're really looking for NTU. So given the outlet temperature, we know epsilon, and to find the right heat exchanger to give that outlet temperature, or the right size heat exchanger, we calculate NTU, and that's the case where we're calculating NTU from epsilon. And generally, this is a similar result as what you would get from the LMTD method. That was a co-flow heat exchanger. For a counterflow heat exchanger, you get very similar effects. For a counterflow heat exchanger, epsilon is also given in terms of NTU and RC, and a typical counterflow equation form is shown here. One of the things that you see, though, is that unlike before, where we had 1 plus RC in the denominator, we have 1 minus RC in the denominator. What that really means is that for a given NTU and RC, as far as giving epsilon, the counterflow heat exchanger is more effective in terms of the overall transfer of heat, since it can support larger temperature differences. You get a larger epsilon from the counterflow system than the co-flow system, given the same NTUs and RCs. If the ratios of C, or the RC, the capacity ratio is very small, then we clearly see that epsilon is just equal to 1 minus e to the minus NTU, which is the result that we got for that single stream case where we had a saturation system or a condenser. So this is the condensing system. If you recall, that condensing system we talked about some time ago. Where we had a single stream, the T sat, T cold in, C cold out. So for that problem, we had this really simple result for epsilon, and for that we can now see is a capacity ratio small condition.